See, one thing that we did not talk about here so far is how to synchronize, right. So for the very first code that we saw, the loop serial code, okay. So in this code actually we were running a for loop and writing onto the same variable in a shared mode by default before we put this private, right. Without this private, actually maybe I'll use the sync unsafe, that's what it's for. So it's the sync unsafe function is basically an unsafe implementation of this function. So it's calling this function. So we'll focus only on this part here. Did I already change anything here? Looks like yeah. Okay, that's fine. Yeah. So let's say here is my function. It's a sum function foo. It's unsafe and right. And then here is my for loop, and the for loop all it does is a equals a plus 1. Okay. So the variable a inside this for loop is used both in read and write mode, right. And what we expect out of it is, let's say that we want a to be, if you run your serial code, what a answer you will get, this parallel code also should generate the same answer. Okay, that's our goal, to exactly reproduce the serial code answer, but in faster runtime. Okay, so here since a is also on the left hand side, concurrent execution in a shared mode for a could possibly lead to thread unsafe behavior, and let's actually see that. So I'm actually printing the value, final value of a here and the time. So let's compile this code and give it a run. So I'll call it sync unsafe as the executable name, and then -f open mp, and then sync unsafe is the code. So once you have compiled, it's a yeah. So I just opened the sync-unsafe.c code. Okay, that's what I was showing you just now. Okay, so this is for synchronization, sync for synchronization. Just wanted to have that. Okay, so now that we have an executable, let's look at the usage. It's also going to ask number of iterations, number of threads, n and p, right. So let's say like 1,000,000 and then 1 thread. The final value is 1,000,000, which is what it should be. Let's do 2 threads. The final value is now different. It's not 1,000,000. If I, what's it? Sorry, I didn't miss that. Yeah. So, and then each time it basically gives a different value. So obviously, you don't want to be using this code, right? So it's thread unsafe because different iterations and the order in which they outbait and so on, they are all different, and some values that get written by one thread could get overwritten and so on. So you're not protecting the variable. That's the problem here, right? How do I write protect it? Well, there are a couple of ways to do this, right? So the easiest way to do this is to define this line, pragma omp critical, meaning you have identified a part of your code, a section of your code, and says here is a critical section. Let only one thread execute that section at any given point of time. I don't care what order, whether thread 5 executes first and then thread 0 executes next and 1 executes later. As long as only one thread executes that section of code at any given point of time, I'm fine. Okay, that's basically the safest way to do it, but also it can be highly inefficient. So let's do that. So all I'm going to do is now here inside the for loop, right where just before I want to do this write, I say omp, pragma omp, sorry, critical. Okay, so here also you can put braces. Actually this defines a block. It's a nice thing to actually define blocks, your regions of your code. So this is your critical region right here. Only one thread will get access. Okay. So I think there is some help here. So this is the code, and yeah. So if we execute this, once we compile it, GCC. So let's execute and see whether at least it's reproducing the same answer every time. So every time it's executing, giving the same answer now, right? With increasing number of threads. So you have made the code thread safe now. It's no longer unsafe. But what you will also see is the time is actually possibly going to go up. So so this execution took only 0.04 seconds. This is taking 0.12 seconds, and this is taking 0.13 seconds. Okay, as you keep increasing the number of threads, those threads queue up at the start of the OpenMP critical block, right? And then one has to, you have to let one at a time, and so the more the number of threads, the longer the queue gets, and it slows down the system. So you want to be using critical section only if you have to, absolutely need to, in other words, right? There is a slightly better way of doing critical section if you have what is called the atomic primitive. This is typically hardware supported. Atomic, the term refers to you take a variable, load it onto your registers, basically the CPU takes it from the register, does an update and pushes it back to the register. All happens in an atomic fashion. It's like a fundamental unit of computation. Okay, so it basically is the same as the critical section, but typically it tends to be faster if you have hardware support for it. Okay. An atomic primitive also has some restrictions. You can't do fancy blocks like this. You only have to have like a simple increment operator or a decrement operator. Okay, so there are some restrictions, limitations to this atomic primitive. There's also a third notion of locks that you can use. So in this, basically we say, hey, we will acquire a lock before we enter a critical section and release the lock as we exit out. So only one thread can acquire a given lock at any given point of time, right? And then so you may ask what is different about the critical section and this. Critical section also internally, you're letting only one thread at a time, right? So all the threads queue up, and then one thread acquires the lock and releases the lock as you exit out, right? So then there's a subtle difference between locks and critical section. Basically, critical section can be seen as you can implement critical section using locks, right? But you can do something more in locks that you can't do in plain simple critical section, and that is you can actually use it like a data level lock. Okay, think of this use case. Let's say I have an array, right? One thread wants to update the third index of the array, another thread wants to update the sixth index of the array. Now they are sharing the array, but they are going to operate on two different locations, and so there is no need for one thread to wait for the other, right? They can concurrently update because they are actually updating two different locations, even though it's coming from the shared variable A, my array, isn't it? So if I put a critical section, I'm basically placing a lock on the entire array, in effect. I'm saying only one thread can access any index of my array at the same time, which means all the threads queue up and you slow down the performance. But what you can do in the lock system is you can initialize as many locks as there are number of indices in your array. Okay, and then if a thread wants to access the third index, it will only go and acquire the lock for that index and then release it as it exits out, which means these locks can be independently acquired, right? Only if you want to access the same lock at the same time you need to queue up. So this gives you a higher resolution at which you can synchronize and hence reduce the synchronization costs. Okay, so that's the difference between locks and so on. So this is the general construct for locks. This is the syntax. We declare this variable OMP lock. It's a type, and then we initialize it. The OpenMP system does it. Basically, it says currently initialized state is the lock is available for anyone who wants it, right? The first thread to request that lock will get it. You do that by setting the lock, and then you do whatever you want to do here. This is your critical section of your code that needs to be safe, and then you unset it, meaning release it on your way out. Okay, so this is my lock variable, right? So the state of my lock variable becomes locked as I enter the region, and as I exit, because of the unset call, it gets released. So the next thread which is waiting for that lock to be available will get that. Okay. So you can play with this. We don't have to do this right away, but the syntax is here, and and actually here if you look at the source code, there is a sync unsafe, which is what we used, but there is a slightly larger code called sync.c. If you open up the sync.c function, it really is going to have 3 varieties of this foo function. One is foo critical, which uses a critical section, and then foo atomic, which essentially replaces critical with atomic, and then the third was foo locks, which basically uses lock, those syntax. So 3 different ways to implement the same functions. You might see differences in performance, so I've timed it. You can play with that and see, right? Okay. Let me get to a couple of other things that I want to discuss. One is on scheduling, and I'm going to briefly go over this. When you have a for loop, one way what we have been doing so far is saying I have 100 iterations to execute, 10 threads to that I have available, so we can associate 10 iterations to each thread, right, to fill up the 100 iterations. That is a static way of determining who gets to do what. Static scheduling, okay? But there are other ways to do it. So let me go to this slide. It will help you to understand. So let's say here is, on the vertical axis is, this is whatever the first thread does, whatever the second thread, third thread, and fourth thread. Let's say there are 4 threads, and we have a total of 8 iterations, 0 through 7. Static scheduling means iterations 0, 1, 2, and 3 will be assigned to, iterations 0 and 4 in this case will be given to thread number 0. So there are 2 ways to do this, right? You can put 0, 1, 2, 3 here, 4, 5, 6, 7, or you can do 0, 1, 2, 3, 4, 5, 6, 7. Both are static, okay? So this one does what's called a cyclic allocation. Cyclic allocation means 0 goes to thread 0. Iteration 1 goes to thread 1. Iteration 2 goes to thread 2, 3 goes to thread 3. And then you cycle back in the world of threads. Next iteration goes to 0 again, then 1, 2, 3, 0, 1, 2, 3. That's why it's called a cyclic allocation. There's a block allocation, which is if the iteration assignment is 0, 1, 2, 3, 4, 5, 6, 7, that's block allocation. Okay? So here the thing is, if it so happens that the iteration number 0 and iteration number 4 are heavy duty iterations, they do more work than the other iterations, then that thread which executes these two iterations will take longer to complete. In fact, here as indicated, it takes the longest, right? So here is a thread that finishes first because it got less work, the less lightweight iterations, and here is the thread that finished last because it got the heavy duty iterations, right? So this is your idle time. For the thread that finished first, it's sitting and waiting for that last thread to finish, right? So we can possibly better load balance this. An OpenMP system by default, if you don't specify anything, it does static scheduling, predetermines which iterations go to which thread, okay? And that may not work when you have variable load within each iteration. So what you do is you specify something called dynamic scheduling, which does a better job of managing the load. It does it in a cautious way. It says, let me first start with giving iteration 0, 1, 2, 3 to those 4 threads. Let's see who completes first. This thread number 3 completed the 3rd iteration before anyone else. So it goes and picks up the next available iteration from the queue. So it takes charge of the iteration 4. The next one to complete is 2. It goes and picks up iteration number 5 and so on. So more importantly, here the time has become, they all complete roughly at the same time. So there's not much of an idle time, right? So you basically, dynamic scheduling determines how to assign workload. And there are, actually you can do it at a higher resolution as shown in this slide. So if, let's say you have static scheduling, by default it's what's called the block allocation. Along this x-axis, let's say there are n iterations, right? Thread 0 gets the first n over p. Thread 1 gets the next n over p iterations. This is predetermined, okay? You can also specify in OpenMP what is a batch size. or a chunk size it's called. So chunk size means that what is the smallest unit of operation. You don't, so n over p is lot of iterations. You can specify in batches, so you have better control over the load. Okay, so in static iteration it says this batch goes here, thread 0, it's in this case a cyclic allocation, block cyclic allocation, that's actually. In time, no, this is the iterations, the number of iterations n.
Yeah, but you're saying that this thread has an execution time?
No, execution, no. So it's number of iterations is what is the chunk size. It's like how many iterations should I give any given thread at any given point of time. That's what a chunk means. You distribute loads in chunk as opposed to distributing one at a time or big groups in time. So basically you say, I have n iterations to run. If I have p threads, I can distribute n over p each. That's at very coarse level distribution. The other extreme way of doing it is distribute one iteration at a time and see who completes first. Chunk size gives you that flexibility somewhere in between. You determine. You give 10 iterations at any given point of time. Say. Right? You specify that. There is a default chunk size. If you don't specify anything, chunk size is n over p. Dynamic is, as the name indicates, dynamics. You still distribute in those chunks, but whichever thread finishes next will pick the next batch or chunk of iterations. Right? It's chunks. These iterations are the work pipeline. You extract work in these chunk sizes and allocate it to the next thread that is looking for work. That's it. Right? All that is handled by the OpenMP environment. Guided is a different scheme which is somewhere between a static and a dynamic. So let's not go into those details, but I'll be very happy to take questions after the session because we are running slightly short on time. I'd like to at least cover one more like higher level application which you might want to look at before we wrap up. Right? So you all are familiar with matrix multiplication, matrix vector multiplication. Right? So let's say I want to parallelize this matrix vector multiplication. Right? So a simple serial code will look like this. I have a matrix M, a vector V, right? And I have to produce another vector as the output, right? So call it X. So here basically you're taking the n columns, n fields. So think of it as an m by n matrix. So n values of this row needs to be multiplied with the n values coming from this vector, and the answers need to be added up and stored in this output vector entry, right? That's what. So your serial code really will have two nested for loops. So how do we parallelize this two nested for loop? I can put an OpenMP parallel for here, or I can put an OpenMP parallel for here. I have two options here. Parallelize the outer for loop or the inner for loop. You want to parallelize the dimension which has more work, typically, right? If I have only 2 rows and 1,000 columns, I want to be parallelizing along the columns because I might want to use hundreds of threads. Correct? Where there is more work, that's where you want to parallelize. Okay. So there are two ways, however, to do that. So this is a rough schematic illustration of how to assign the computation, who does what, right? So here is my m by n matrix, and then n by 1 vector, and here is my output vector, right? And one way to do is what is called the row decomposition. Let's say we have 4 threads. We say, okay, thread 0 will pick up the first batch of m over p rows. The next batch of m over p rows will be given to the next thread. The next batch of m over p will be given to that thread, and so on. So in other words, we take a block, equal size blocks of rows, and assign it to each and every thread, so that we cover the entire matrix, right? When you do that, what happens is you take any row from here, it's handled by a single thread, which means it can do the multiplication internally against this vector and record the answer here, right? So essentially there is no need for synchronization here. Every thread will operate on, at any given point, a row, multiply it with that vector, store the answer there. that's happening independent of what some other thread is doing, because those threads are working on other rows, correct? So obviously this is a good way of doing. So each thread gets m over p rows, time taken is proportional to m times n is the total volume of work, right? We have p threads, which means each of these sub rectangles are mn divided by p. It's equal size blocks, right? So that's how much time our code will take. This code will scale if you implement it this way, and there is no need for synchronization here. One thread doesn't need to talk to another thread, okay? But there is a slightly different way of doing it. In this case, instead of doing a row decomposition, we can also do column decomposition like this. You can assign threads, you can assign a batch of columns to each thread. So n is the number of columns, p is the number of threads, so n divided by p will be the number of columns each thread gets, right? This actually you would do if the number of columns is very high and the number of rows is very small, right? In the case, let's say there are only 10 rows, but there could be a million columns in my input matrix, right? I want to be parallelizing along the column, not in the row, because I might want to use more than 10 threads, right? So in that case, column decomposition makes sense, but we have to be a little careful here, because if you take any row that's here, this part of the row is handled by one thread, and this part of the row, same row, is handled by a different thread, which means they will all be multiplying different parts of the vector, and they will all be producing a partial sum, and you want to be reducing that. You want to add those partial sum to create your global sum, which should go there. This strategy will make you use the reduction operation. So here the work is, the time is proportional, is taken for each thread is proportional to mn over p plus the time required for reduction. But fortunately, reduction is a low cost operation. It's a log p. So you would still see this code scale, but not as good as the previous code, okay? So these are two high level strategies you can deploy. Then of course we go into the gory details of how to actually program this, make this work, how to allocate who does what, right? So that's left as exercise, I would say, at this point, right? We don't have time for that, but you can play. In fact, if you go to your code and there is a matrix vector dot c, we have written this code to essentially implement, first basically you generate a matrix in memory, so you don't have to read it from a file. It doesn't matter, right, what matrix it is, just for testing purposes. And then we generate a vector in a random fashion, and then we do a multiply and then record the time. So multiply is the main function here, right? And I've implemented two functions here. Multiply here is row wise decomposition, and multiply with column wise decomposition. And column, it uses the reduction. There's no need for reduction in the row wise because you never split a row.